Hi everyone. So in today's video we are going to discuss the topic of grouping of cells. So basically whether it is grouping of resistor or grouping of capacitor or now grouping of cells, these are grouping of two types. One is series grouping and the other one is parallel grouping. Okay, in capacitors we have seen capacitors in series and parallel. Resistors we have series and parallel grouping of resistors. Now here also in cells we can arrange cells in series or we can arrange cells in parallel. Okay. Now we'll see how the combination works when they are arranged in series and then they are arranged in parallel. Okay. And what is the advantage of using cells in series or using cells in parallel. Okay. Then in the later part of the video we will also see what happens when we have mixed grouping of cells. Mixed grouping means cells will be arranged both in series as well as parallel. Okay, so let's start. So first we'll study about series grouping of cells. Okay, cells in series. Okay, now see, first of all we need to know or revisit the fundamental concept. The fundamental concept is, like, suppose this is a cell of EMF E. Okay, and suppose this is the internal resistance of the cell. Internal resistance of the cell. Okay, now suppose this is terminal A and this is terminal B. So at A the potential it is VA, at B the potential is VB. Okay, so previously we have seen that the relation between EMF and terminal potential difference, it is given by E is equal to V plus I into R, where E is the EMF, V is the terminal potential difference, I is the current and R is the internal resistance. Or I can write this as V is equal to E minus IR. V is equal to E minus IR. So V is the terminal potential difference. That is potential difference across the cell when current is being drawn from the cell. Okay, so suppose this is a part of the circuit, but we are only studying this portion. So suppose this is high potential, this is low potential. So current will flow in this direction from B to A. So suppose this I is the current. Okay, so this is the current I. So for this we will write VA minus VB. That is the potential difference across this cell. It is equal to E minus I into R. This is the basic concept. This is what we know. Okay. Now we have cells in series. Okay. So suppose we have two cells connected in series. Okay. So the series connection, a proper series connection will be like this is the positive terminal, this is the negative terminal, this is the positive terminal and this is the negative terminal. Okay, so this negative terminal and this next cell is this positive terminal. So this is how we connect cells in series. Okay, you might have seen this in torch. Okay, torch where we have more than one cells. So this is how this cells are connected. Okay, now suppose this is of EMF E1, this is of EMF E2, and suppose R1 is the internal resistance of this cell and R2 is the internal resistance of the second cell. Okay, so suppose this is A, this is C and this is B. Okay, so now we have two cells connected in series. Okay, now suppose this represents the equivalent EMF of the two cells, means this cell represents the equivalent of these two cells. So I will write this as E equivalent and this R is the equivalent internal resistance. So I will write it as R EQ, equivalent. So this circuit is the equivalent circuit for this. Okay, so our goal is to find E equivalent and R equivalent EMF and equivalent internal resistance. Okay. Acha. Now across this first cell, this cell, I can write VA minus VC is equal to, this is the direction of current. See, both the cells are connected in series. So series we have, how do we identify circuit elements in series? Series we have same flow of current, same current flows. Okay, so here obviously same current has to flow because from here to here only one path is available. So if current comes from this direction, it will go in this direction. So same current will flow through both the cells. So VA minus VC, if I is the current, suppose I is the current, so I is the current flowing through both the cells. So VA minus VC for this part is VC equal to E1 minus IR1. Okay. What about this? This part, it will be VC minus VB is equal to E2 minus IR2. Okay. So if we add these two, so this VC gets cancelled. So VA minus VB is equal to E1 plus E2 minus IR1 plus R2. Okay. Now if we compare this with this, so here this E is E equivalent. So this is E equivalent. This is R equivalent. So this is the equation for this circuit, and this circuit is the equivalent circuit for this circuit. So if we compare, suppose this is equation 1 and this is equation 2. So if we compare these two equations, see, this is E equivalent, this is E1 plus E2. So E equivalent will be equal to E1 plus E2. Okay. Similarly, R equivalent will be R1 plus R2. So this is how you can calculate the equivalent EMF. So suppose this is 2 volt, this is 2 volt, and they are connected in series. So equivalent EMF will be 4 volt. Okay. And internal resistance, see, obviously, see, this internal resistance is a resistance. So resistance in series means total resistance will be R1 plus R2. Okay. So this is cells in series. Okay. This is one way of observing this cells in series. We will see one more way later. Okay. But this is the basic concept. Achha, next, let us see the topic of cells in parallel. Grouping of cells in parallel. Okay. So for that we have two cells. Suppose this is cell of EMF E1, internal resistance R1. Okay. Another cell of EMF E2, internal resistance R2. Okay. So this is the grouping of two cells in parallel. So this is the positive terminal, negative terminal, positive terminal, negative terminal. Positive terminals are on one side, negative terminals are on the other side, same side. Okay. Acha. Suppose I current is coming from this side. Current will flow like this. Okay. So current goes into the negative cell terminal and comes out to the positive terminal. So this I current, now two paths are there, two paths, available paths. So current flowing through this path is I1 and current flowing through this path is I2. So this I1 current comes like this. This is I2. So I1, I2, again this becomes I. Okay. Now this is at potential VA. This is at potential VB. Okay. Achha. Now for this path, we can write the equation for VA minus VB as, see, terminal potential difference is equal to EMF minus current into internal resistance. This is the basic equation. Okay. So VA minus VB is the potential difference now. So it is equal to E1 minus I1 R1. Okay. So similarly, I can write VA minus VB for this part, this second cell of EMF E2. It is equal to E2 minus I2 R2. Okay. Achha. Now from this I can write I1, value of I1 as this will come to this side. So VA minus VB by R1 minus E1 by R1. Correct? Similarly for this, from this I can write the value of I2 as minus VB by R2 minus E2 by R2. Okay, now if I add these two equations, what do I get? I'm writing here this I1 plus I2. Okay, so this is, I'm adding here. So I1 plus I2, it is equal to VA minus VB. Take it as common, 1 by R1 plus 1 by R2, 1 by R1 plus 1 by R2, and then minus E1 by R1 plus E2 by R2. Okay, so now see, this I current branches out as I1 and I2, so this I is equal to I1 plus I2, I is equal to I1 plus I2. So I can replace this I1 plus I2 as I. So I is equal to this quantity. Okay. From this I can write I is equal to VA minus VB. This is R1 plus R2 divided by R1 R2 minus E1 R2 plus E2 R1 divided by R1 R2. Correct? So now rearranging, and taking these terms to the other side. So we have VA minus VB times R1 plus R2 divided by R1 R2 is equal to I plus this term E1 R2 plus E2 R1 divided by R1 R2. So now if I find the value of VA minus VB from this, what do I have? VA minus VB is equal to, I have to multiply this R1, this term, R1, it will go to the other side. So this is I times R1 R2 divided by R1 plus R2. Okay, and this becomes, this R1 2 gets cancelled. So this is plus E1 R2 plus E2 R1 divided by R1 plus R2. Okay, so we have this VA minus VB is equal to this term. Okay, now if we have to find the equivalent EMF of these two cells, then I need to draw the equivalent circuit for this. So that is a single cell producing the same effect as the given two cells. So this is E equivalent, this is R equivalent, this is VA, this is VB, and current I is flowing. I current is the total current flowing in the circuit, isn't it? So from this I can write VA minus VB, it is equal to E equivalent minus IR equivalent. Okay. So along with I, we have this term. Equivalent EMF, we have this term. So that means if we compare these two, what do we have? We have R equivalent, it is equal to R1 R2 divided by R1 plus R2. Okay. Now see, we have burned so much of calories to find this equation. But actually this was known, because see, what is this? This is 1 by R equivalent. It is equal to 1 by R1 plus 1 by R2. And it has to be, because see, this is resistance R1, internal resistance R1, this is internal resistance R2. They are in parallel, so this is the equivalent internal resistance. Okay, and this E equivalent, that is equivalent EMF, that is given by this term, so that is E1 R2. R2 plus E2 R1 divided by R1 plus R2. Okay. So this is the expression for equivalent EMF. Expression for equivalent EMF. And this is the expression for equivalent internal resistance. Okay. So now we have studied grouping of cells in series and grouping of cells in parallel. Okay. Now let us have another approach to this grouping of cells. Okay. Now first we'll see cells in series. Okay. Now here, instead of having two cells, suppose we have n cells. Okay. N cells. These are n identical cells. N identical cells. Okay. N identical cells. So each of EMF E and each of internal resistance R. Okay. And suppose this is connected to external resistance capital R. Okay. So all these are in series. So what will be the net equivalent resistance, internal resistance? R equivalent, it will be equal to R plus R n times. So that is equal to NR. And see, if these are in series, so this is current I. So this I current will flow through this also. So same current is flowing through these cells and also through this resistance. So all these resistances are in series. So what will be the total resistance? R equivalent, it will be equal to R plus NR. And all cells are in series and each of EMF E. So what will be the net EMF? E equivalent, it will be equal to N times E. Correct? N times E. So what will be the current, equivalent current, this current I? I is equal to net EMF divided by total resistance R equivalent. So I is equal to, this is NE divided by R plus NR. So this is the current that will flow in this combination of cells, n identical cells. Okay. Acha. So now see, we have I is equal to NE divided by R plus NR. What is R? R is the external resistance. What is NR? That is total internal resistance. Total internal resistance. Okay. Acha. Now suppose here we have two possibilities. One possibility is when R is much greater than NR. That is, external resistance is much greater than the total internal resistance. So if R is much greater than NR, I can write R plus NR as approximately equal to R, because R is much greater than NR. So this current will be NE divided by R, approximately equal to NE divided by capital R. Okay. This is one condition. Another condition is when R is very much smaller than NR. That is, external resistance is much smaller than the total internal resistance. Okay. So in that case, R plus NR will be approximately equal to NR. So in that case, I will be approximately equal to NE by NR. So that is I approximately equal to E by R. So the cell will behave as if only single cell is working. Single cell of EMF E. Okay. Acha. So this is one extremity. This is another extremity. Correct? With regard to the resistances, this is one extremity. This is the another extremity. For this extremity, when R is much greater than the total internal resistance, we are getting current as N times E by R. N times for N cells. Okay. So that means this current is going to be the maximum current. This current is going to be the maximum current. Achha. Now you may ask why I am finding the condition for maximum current. Because for cells in series, for n identical cells in series, if you want to draw maximum current from the circuit, this is the condition. External resistance should be much greater than the total internal resistance. So in that case, this current will be maximum. So for series grouping of cells, the current from the cell supplied by the cell will be maximum when external resistance is much greater than the total internal resistance. This is the total internal resistance. Okay, this is the total internal resistance. So when external resistance is much greater than the total internal resistance, we will get maximum current for cells in series. Okay. So next, let us see the same approach for grouping of cells in parallel. Okay, cells in parallel. So again we have identical cells. Okay, all are identical cells. So this is EMF E, internal resistance R. So we have such n cells. We have n rows, each row with one cell. All the cells are identical. So each of EMF E, internal resistance R, and this combination is connected to external resistance capital R. Okay. Achha. Now see, this is R. N cells are there. N identical cells. Or suppose we take, instead of N, let us take M cells. In series we have N cells, here M cells. Okay. So we have M identical cells in parallel. So what will be the total internal resistance? R equivalent, 1 by R equivalent. These are in parallel. This combination, this combination is sending current I. So this combination is having an internal resistance R equivalent. So 1 by R equivalent, it will be equal to 1 by R plus 1 by R plus this is M times. Correct? So this is R equivalent, it will be equal to R by M. Correct? R by M. Achha. Now this is connected to this external resistance R. So this combination is sending current. So this combination is carrying current I. So same current flows through this. So this combination is in series with this. So the total resistance will be R equivalent. It will be equal to R plus R by N. R plus R by N. Now each cell is of EMF E, but they are in parallel. So what will happen? What will be the net EMF? It will be E. Okay, because parallel potential difference remains same. So EMF also remains same. So E equivalent, it is equal to E. E equivalent, it is equal to E. So what will be the value of current? What will be the value of current? This current. Current supplied by this combination of M cells, M identical cells in parallel. So I will be equal to E equivalent divided by R equivalent. Current equal to voltage by resistance. Simple relation. So this is equal to E divided by R plus R by M. Okay. So this is the current, net current that is flowing through this resistor supplied by the combination of M identical cells. Okay. Achha. Now, so we have the expression for current. Okay. So let me write this expression over here and then again identify the condition for maximum current. Condition for maximum current. Okay. So what is this? This is the external resistance and this is the total internal resistance, isn't it? So I can write this as, see again, two conditions when R is much greater than R by M. What is the meaning of this? This means external resistance is much greater than the total internal resistance. And the other extremity will be R much smaller than R by M. That is, external resistance much smaller than the total internal resistance. Okay. So if we use this condition over here, so this R plus R by M, this will be approximately equal to, since this is much greater, this will be equal to R. So this current will be equal to E by R. E by R. And what about this? This becomes approximately equal to R by M because now this is greater. So if you substitute this over here, we get I is equal to E divided by R by M. So this M goes here. So now this is M times E by R. Okay. So M times E by R means this, obviously this is a large current. So this is the maximum current. This is the maximum current. And this is the condition for maximum current. This is the condition for maximum current. So for parallel grouping of cells, for parallel grouping of M identical cells, if you wish to draw maximum current from the grouping of cells, then the condition is the total internal resistance of the cell combination must be much greater than the external resistance. Okay, so this is just the opposite to what we got the condition for maximum current in series grouping of cells. Okay, so this is the expression for equivalent current, and this is the expression for maximum current, and this is the condition for maximum current. Okay, so now we have got the condition for maximum current in series grouping of cells and parallel grouping of cells. Okay, now there is one more grouping of cells, that is possible grouping of cells, that is called mixed grouping of cells. Okay, so now let us see how the mixed grouping of cells looks. So this is cells in series. So here we have n cells. Okay, all are identical cells. So again another row, again n cells and identical cells. So each of EMF E internal resistance R. Okay, so suppose there are such m rows, okay, m rows, they are in parallel. This is series grouping. So we have cells in series, cells in parallel. So this is called mixed grouping. Mixed grouping. Okay, so all the cells are identical. So each is of EMF E, internal resistance R. Okay, so see, in one row we have n cells. We have n cells, and there are m rows. So what will be the total number of cells? It will be m into n. Okay, so total cells is m into n. Total cells is m into n. Okay, acha. Now what is the internal resistance of one row? R n times. So it will be nr. This will be nr. So all nr's. Now this combination is connected to external resistance R. Okay. So this is nr, n times. So the total this equivalent internal resistance R equivalent, I can write this as nr by m. Okay, so n cells in each row, so that is nr. M rows are there, so R equivalent equal to nr by m. This combination, see, this represents the equivalent resistance of this part. Now this part is sending current I through this resistance. So that means this combination which is in series with this. So I can write R equivalent, it is equal to R plus NR by M. Okay, acha. Now for one row, N times. So what will be the equivalent EMF? NE. So for this it is NE, for this it is NE, for each row it is NE. So total, they are parallel, so total will also be NE. So equivalent EMF, it is NE. Equivalent EMF is NE. So from this, we get the current as E equivalent by R equivalent. So that is equal to NE divided by this quantity. So this R plus NR by M. Okay. So I can write this as MNE divided by MR plus NR. Correct? So now this term can be rearranged as I is equal to MNE. This denominator term, I will write it as root MR minus root NR square plus 2 times square root of Mn RR. Okay. Achha. So now, see, if I need to find the value of maximum current, so this current will be maximum when denominator will be minimum. Now, denominator will be minimum when this quantity is 0, correct? And this quantity will be 0 if this is equal to this. Okay, means MR, it is equal to NR, or R is equal to NR by M. NR by M. What is this? R equal to NR by M. What is this? R. What is NR by M? NR by M is the total internal resistance. So here this current will be maximum. See, for this current will be maximum and denominator is minimum. So to minimize the denominator, I will make this quantity as 0. Correct? Now for this quantity is 0, that means R equal to NR by M. So that means current supplied by the mixed grouping of cells will be maximum when external resistance is equal to the internal resistance of the cell combination. Okay, so for mixed grouping of cells, current supplied by the cell combination will be maximum when external resistance is equal to the total internal resistance of the cell combination. Okay. So we can summarize this result as, see, series combination is useful when internal resistance is less than the external resistance. Okay. Or we can say external resistance is greater than the internal resistance. Parallel combination is useful when internal resistance is greater than the external resistance. Okay. And so the conditions are just the opposite. And mixed grouping, what happens? When external resistance is equal to the internal resistance, the current is maximum. Okay, so these are the conditions for maximum current for series grouping, for parallel grouping and mixed grouping. So series combination is useful when internal resistance is less than external resistance. Parallel combination is useful when internal resistance is greater than external resistance. Okay, mixed grouping, current is maximum when external resistance is equal to the internal resistance. Okay. So now one more thing, like suppose you have these cells in series. Okay, so these are 3 cells in series. So the correct connection for cells in series is, like, see, this is the positive terminal, this is the negative terminal, this is the positive terminal, this is the negative terminal, this is the positive terminal, this is the negative terminal. Isn't it? So suppose this is 2 volt, this is 2 volt, this is 2 volt. Means EMF of the 3 cells, 2 volt, 2 volt and 2 volt. So what will be the net EMF? Net EMF, it will be equal to 2 plus 2 plus 2. So that is equal to 6 volt. This is the correct connection. Now what happens if the cells are wrongly connected? So suppose one cell is wrongly connected. So this wrong connection means, so this is the wrong connection, and suppose this is properly connected. So this is positive, negative, negative, positive, positive, negative. Okay. So this is 2 volt, 2 volt, 2 volt. Okay. Achha. Now if we calculate the net EMF here, E net, it will be 2, this is plus 2, this will become minus 2, this is plus 2. Since this is connected in the opposite direction, so this will be minus 2. So now E net, it is equal to how much? 2 minus 2 is 0, plus 2, so this is 2 volt. Okay. Achha. So how can you generalize this? See, when one cell gets a wrong connection, it affects another cell. See, this because of this is becoming minus 2, this 2 gets cancelled. So 2 cells are getting removed in air effectively. So in general, we can say that suppose you have n cells, and out of n cells, m cells are wrongly connected. Total n cells are there. Out of n cells, m cells are wrongly connected. So in this case, the net EMF, it will be equal to NE minus twice ME. So such that E net, I can write it as N minus twice M into E. This is again, we have assumed that the cells are identical, means EMF is same for all. Internal resistance is also same. Okay. See, you can use, you can check, verify it. See, here we have how many cells? 3 cells. Total 3 cells. Okay. So E net, it is equal to N is 3 minus 2 times, how many cells is wrongly connected? 1 cell. So M is 1 times EMF of 1 cell is 2 volts, so this is 2. 3 minus 2 is 1 into 2, so this is 2 volt. So this is how you calculate the net EMF when out of n cells, m cells are wrongly connected. Okay. Achha. But see, when you connect them in opposite order, the internal resistance doesn't change. Okay. So here the internal resistance, suppose the internal resistances are, okay, for this condition, suppose there are n cells. So what will be the total internal resistance? Total internal resistance will remain NR. This is not going to change. Okay. So in that case, if we are calculating the current, it will be N minus twice M into E divided by NR. Okay. So this is the expression for current. In resistance is not going to change. It is only the EMF that is going to be affected when cells are wrongly connected. Okay. So the general formula is N minus twice M into